When I was invited to speak here, the conference page was a bit low-key, and I thought this is a great opportunity to practice my PyCon US talk in front of a bunch of friends. Then I thought it's like 500 of you, which is probably more that will ever come to my talk at PyCon US. So I guess this is the real thing now, so no pressure on me at all. Anyhow, a quick cultural question. How many of you do get the MGS? 1, 2, 3. Okay. You don't count, Andrew. You're not part of this culture. Okay, so I'm glad the schedule is already down the drain. Everybody's running late, so I will probably run late too. I've already apologized to Joshua about that one. But I'm here to talk about last year, or more concretely, my last year. Because last year, after PyCon US, which took place at the west coast of the US, I took advantage of being there, because I'm from Berlin, so I'm European, and for me, it's a very long flight to get there. There's a big jet lag involved, so I wanted to enjoy the west coast, and I took a road trip from San Francisco to Los Angeles, up to Las Vegas, back to San Francisco, and before I flew back, I made a tiny little small detour to Hawaii. That meant that I was 5 weeks away from work, if you take all together. And with every new photo I tweeted, more people kept asking me if I still have a job and if I'm gonna ever work again. Now, and that is exactly here at the airport of Kauai with a $7 plastic cup of beer in my hand when this talk was conceived. Because I do indeed still have a job, and I have almost 70 projects which I'm responsible for. So to put it in other words, I know basically nothing about scaling systems to Instagram scale, but I know not everything, but I know a lot about how to make my projects and my systems to work in a way that I get any sleep at all. So, of course, it makes it my story. It's subjective. It's things I learned the hard way in the past 10 years, because that's how long I'm doing my job right now. And some things, at least one of the things will come obvious to every one of you. But I will touch on a lot of topics, a lot of them. A lot of them are more DevOpsy in their nature, but a lot of them are also about software engineering in general and reliability topics. And at the end of the talk, there will be a page, a link, with all the topics I'm talking about and further literature for you to study at your own leisure. So you do not have to take any notes in that sense. So let's see what we can do to avoid unnecessary outages. So first, and that's usually with everything, you have to change your attitude, probably, if you have problems. Because you will have to spend a significant time on non-features. And talk is cheap, because if you ask someone if reliability is a priority, they will tell you that it's top priority, because everything is top priority. But if you do not have enough time to write tests, or you do not have enough time to instrument your system and your software, it's just a lie, it's hypocrisy. That's like a construction company that says that safety is our top priority, and the workers have to buy their own safety wear. So, reliable systems take time. And if your only job performance metric is shipping new features, you're going to have a problem. However, there is hope, because reliable systems are not only about having a nice vacation, but there's a solid business case to be made. And that one is that the fewer urgent interruptions you get, the more work can you do on important stuff. Or put it the other way around, given enough unreliable systems, nothing new will ever get done, because everyone is just busy firefighting and trying to keep the existing infrastructure running, which is a pretty common story you hear when you talk to people working at those unicorn startups. So the problem is it takes still long-term thinking. That's not super common in our line of work. Startups often don't even have the luxury of spending a lot of time on things like that, because they don't even know if this thing will pay off eventually, so they have to prototype fast. Now, all that said, let's get a bit more practical. And in my first point, I'm going to defer to authority. I will defer to Tony Hoare, who invented Quicksort and many other great things in all things concurrent systems. But Edsger Dijkstra said basically the same. So the price of reliability is the pursuit of the utmost simplicity. And this is true at any level. It doesn't matter if you're writing firmware for a piece of hardware or if you are writing JavaScript front-end applications. So one important distinction that has to be made is that simple and easy are almost opposite things. Because an easy solution almost never is simple, and simple solutions are very hard to find, so they are not easy to find. And a good way to approach simplicity is to go from the other side, from complexity. So, and I think all goes down to how many things, how many concepts do you have to keep in your mind if you are trying to reason about a system, about a class, about the infrastructure, when you want to make changes to it, when you want to understand it. How many things, concepts do you have to juggle? Because people are naturally limited in things they can keep in mind, they can juggle. And that's why there's the term of normal accidents, which has been coined by Charles Perrow in the wake of the 3 Mile Island incident, which was a nuclear plant, accident. It's not as bad as what happened here in Chernobyl, but it was pretty bad. And it's called normal because it's inevitable in a highly complex, tightly coupled system that there will be an accident eventually. Now, if you take it a bit more graphically, and assuming you're writing a web page or a web service, and every request has to go through a machinery like this one, it's impossible to reason about how a change will affect the whole system. It's impossible to reason about what a part is actually doing. And there's also a lot of parts that can just break. And as you can see, there's a lot of connections, so it's most likely they will take everything down with them, which is a problem. And the irony is, if you have such a system and you want to make it safer, you're going to make it more complex, which means that you will make it even more likely to fail. So that said, you have to differentiate between 2 types of complexity. And the difference is very important. So first, there's the essential complexity, which is inherent to the problem you are solving. So that's what you're getting paid for. Someone tells you solve this problem, and this problem has a complexity, that's the essential one. But there's also the accidental complexity, which is something that you do to yourself. It can come from wrong abstractions, from cumbersome deployment procedures, or just using inadequate tools, like Python 2, for example. I would drop my mic, but it's wired to my head. So ask yourself, how much time do you spend on accidental complexity? How much of your energy goes in there? And that is not 0 for anyone. It's not 0 for me either. I spend weeks fighting accidental complexity. But it's always good to take a step back and look at this. Now, what is simple software? So it's a bit like ravioli. This is not my metaphor, but I really like it. If you have a good software design, you have a lot of small, independent objects or functions that do as little as possible and that are as self-contained as possible. So in ravioli, if you cook them right, the filling stays inside. The fillings do not mix. So they are self-contained, they have a clear interface which you program against, and they are super easy to test because you have very small parts with very little complexity. Now, on the other side, bad design. What do we have there? We have big classes. We have God objects. God objects because they know too much, they do too much, and they are they're very hard to test because you need a test harness to even instantiate such a class. And they are pretty common, even in popular Python projects. Now, once you entangle yourself in big classes and God objects, you are solving a lot of accidental problems very soon too. Now, I do not like the word magic. People like to use it to defame things, but I do not like it. It's subjective. And something that was magic yesterday may be best practice today. However, I really do not like techniques that save you some typing, and in exchange, they make it more difficult to understand your software and your system. And I think the biggest perpetrator in Python for that are meta classes. So meta classes are a little bit like monads in Haskell, because nobody really understands them. Then people put all this effort to understand them, and then they write a blog post about how great meta classes are and how easy they are to use. But in practice, you usually just pay complexity, and you just get some syntactic sugar in exchange. So usually they are not worth it. Another less accepted guilty party is subclassing. Subclassing was made for specialization. It was never intended for code reuse. But that's exactly what people are usually using it for. And if you do that, you run into problems eventually. But we are so trained because you have an animal, and the dog is an animal, but it doesn't make any sense, usually. Well, if you need to specialize, feel free to subclass, but do not build a design around of it, because you will regret it. I don't know how many of you ever used Twisted? Okay, quite a bit. So do you remember when you started using Twisted? I don't know about you, but for me the biggest hurdle was to understand what all these classes do and where the methods are coming from and the attributes, because Twisted is a child of the early 2000s, so it has a very wide and very deep inheritance hierarchy. So when you have a protocol, it's a subclass of 5 other classes, and some of them you use, some of them you can't use, and this is exactly what subclassing does to you. So the magic keyword is composition, actually. And composition over inheritance is not a new concept, but it's still kind of hard to sell. And in Python, we have another awesome thing, which is called class decorators. And they are superior to inheritance in many ways. For example, they're explicit on the top of your class. They have an order, so you can reasonably reason about how they are applied. So I usually prefer them. In normal programming, you usually do not need to subclass. And I stopped doing it quite a while ago, except, of course, exceptions, or when you're doing low-level stuff where you need certain characteristics. But anecdotally, when I'm revisiting a project that does not subclass, after a year or 2 years, which happens to me, it's much easier to understand, because everything is explicitly written down in one place. And there, you don't have to take my word for it. There's been a great talk at PyCon a few years ago, which is called The End of Object Inheritance. And it's 2 Googlers who explain everything much better than I ever can, so I encourage you to watch it. It's, of course, on the page I've mentioned. So, however, if you find writing Python classes tiresome, I am on the same page. And that's why I wrote RETRIES. How many of you know RETRIES? Not enough. Not enough. So RETRIES will write class boilerplate for you. So dunder init, dunder wrapper, equality, identity, and all these things. You just define your attributes on a class in a declarative way, and the methods are being written. So it's similar to name tuples, except that name tuples are terrible and were never intended to be used as class replacement. But people do it because it's convenient and it's easier than to write a proper class. RETRIES, there's no magic, no subclassing. It will just write methods for you and attach it to a class. So you have a completely simple object like any other else. You do not have the tuple type in your inheritance tree. So, end of advertisement. You should check it out. The next point is operational complexity, which is the complexity of running your infrastructure or parts of your infrastructure. And I don't think it's controversial to say that distributed systems are hard. But let's have a look. I think this is a fairly standard architecture. And it's a good architecture. You have a client that talks to a CDN, which is usually not part of your infrastructure, but it talks also to an application, which has a work queue, a database, and a Redis cache. Now, every single box here is a point of failure. But wait, there's more. Every link between those boxes is a point of failure too. So at this point, we have 10 independent points of failure, which is kind of bad, because they're more or less adding up the risk. And that's all because network partitions are a thing. And For example, Google, if they're set up a new cluster, in the first year, they have 3 router failures, 8 network maintenances, 12 router reloads, and I'm running out of fingers, 40 to 80 machines see a 50% packet loss. So they are rare, but they happen. And at scale, rare events are a common event. So think twice before you add new boxes and new links, because every new component you add to infrastructure introduces new and exciting ways for failure. So let's talk about microservices, because that's about splitting up your application into many small web services. It has a lot of upsides. I'm not going to enumerate them here, but they also add many more red boxes and many more red arrows. And the arrows don't go just in one direction. They are going all across over themselves. Now you go from a big monolith, which has some bad properties for sure, but you have a highly distributed system. And you have an onslaught of new problems you didn't have before, like service discovery, remote logging, tracing. You should not have microservices without a proper tracing infrastructure in place, and all the other fallacies of distributed computing. So what you really want, what you really need, are boundaries. You need to define and adhere to boundaries between modules, between packages. I've touched on this already with Ravioli. So once you've established boundaries, it's also easy to migrate to microservices because the boundaries are already there. You just have to change the way they're interfacing. And there is a place for microservices if you need to scale out, or if you have a heterogeneous systems like we do. We have Perl and PHP in our infrastructure. How they're going to talk to each other? Well, microservices. But it shouldn't be the first step to spin up a bunch of Docker containers that just do one thing. Now, all that said, complexity is reality. It's not the devil, but it's a price you pay for getting stuff done. So for example, Kubernetes. Kubernetes is great, but it has a very high operational complexity. And don't get me wrong, everyone can set up a Kubernetes cluster. Even my dog, and I don't even have a dog. It's very easy. The problem is keeping this infrastructure running, all those etcds and flannels and you name it. So the thing is, though, if Kubernetes has a good overlap with your problems, it's probably worth it. But then you need to have the ability to also run it. So you have to see it more like a currency, and you are the one who defines the budget. And the budget are people. The budget is money. If you, on the other hand, start avoiding complexity at any price and try to re-implement everything yourself in the simplest possible way, well, then you have the not invented here problem, and you're not going to get anything done anytime. OK. Next one. Plan for stupidity. And this is clearly a hyperbole, because I don't think people are inherently stupid. At least not people who are working for you. Otherwise, why did you hire them? But things seem stupid sometimes in hindsight. And people act stupid sometimes. For example, if they're sleep deprived because the baby cried all night, or they're at a busy airport and try to redeploy an application before they board their plane, and then they make a mistake. These kind of things happen. That happens to every one of us. Now, I would like to join John Alspaugh and his sentiment that I do not believe in human errors. I believe that if a human causes an outage, there was a system in place that failed them. So think about the S3 failure a few months ago, where half of the internet went down. Now, if you read the postmortem, which you should, it's very interesting, you will see one thing. The outage was caused by a human using a tool in a wrong way, but the postmortem did not blame the human. The postmortem made clear that they need to fix a tool. They need to fix their procedures. And that's how you should think at it, about this kind of things. Because when you build tools and APIs, you should always assume that the operator is drugged from the dentist, consoling a crying baby, or just hasn't slept for 48 hours because there are new medications that their body hasn't adapted to yet. Because if it takes one click or one API call to delete all your data, someone will make that click, that API call. Maybe they will just try to clean their phone screen or something, but the click will come eventually. So don't put it there. And this is similar to products for handicapped people, like accessible products. They are better for everyone. And this is the same. If you build tools that take into account the sense of humanity, you will get better tools. So if you add sharp edges, do not complain if someone hurts themselves or if they hurt you with that. So a nice intersection of sharp edges and complexity is illegal state. By that I mean class instances that end up in an illegal state, so they cannot do what they are meant for doing, because somehow the attributes have values that don't make any sense. And I think the best solution to that is to make illegal state unrepresentable inside. So your objects always have a valid state. So you do not have to track your state inside of your objects, which means less complexity, which means less room for failure. Did I say more complexity or less complexity? It's less complexity. So what do you have to do? You have to be always valid after initialization, and you have to prevent mutation to illegal. Now the first part is easy. Don't do this. Do not allow partial initialization. Because this connection object now has to add extra complexity to check if it's connected. And that means that you have a lot of if statements in your classes. And I'm with Sandy Metz, who said that if statements are a bit of a code smell, and they only get worse. So if you end up with a class that is full of if checks left and right, you may be using the wrong abstraction. And also, what even is a connection before it is connected? It doesn't make a lot of sense. So I believe an initializer should always just return valid objects. You can do, and should be dumb. You can do validation of those attributes, that's fine, but not anymore. And for God's sake, do not do any I/O in your initializers. That makes your objects untestable right away. So please do not do that. So my favorite solution to that are class method factories. They give you a nice API. It clearly says connection point connect, so I know immediately it's connecting, right? If you just use the initializer for that, you wouldn't know what it's doing afterwards. So here by looking once at it, you know what's going on. And if you're like async I/O, and I love async I/O, this helps too because you just add an await in front of it, and there you go. You cannot have asynchronous initializers, and I hope you will never have, because don't do I/O. So you have a nice API. Dunder init, I often treat it like a private API at this point. It just takes all the objects it needs, and this gives you a nice way to abstract away internal data structures like sockets and I/O, of course. And it makes it really highly testable because you can just pass into a fake socket or something, and the initializer will not mind. Another common approach is the builder pattern. It just uses a separate object for configuration. I think it's more common in the Java world, but I've seen it in Python too. So you have a builder, which you tell about your requirements, and then you have a connect call at the end. And if you pass it invalid data, it will fail. Now, prevent mutation to illegal. So you can do that using properties, state machines, and a lot of if statements, but I find it a bit too fiddly, and it adds complexity again. So I prefer to not mutate my instances at all. It's not always possible, but if you can, it's a much nicer experience. And it's the functional programming approach. So you don't give your users any APIs to actually change the instance, but you give them APIs to create new objects based on new parameters. And of course, in Python, it's impossible to have really immutable objects. I mean, address has support for that, but in the end, you can always circumvent it. You can just use object.setAttr, and you can change anything. So I prefer the approach of being a consulting adult and just give people good APIs. So your abstractions can be perfect, but the data that is coming in is usually not perfect. And it can be malicious or it can be a mistake. It doesn't really matter. You have to be careful what you're letting in. And at this point, I disagree with Postal's law, which says to be conservative what you send and be liberal what you receive. I'm saying be always conservative. And this, by the way, was neither malicious nor a mistake. That was literally the only thing I liked about San Francisco. Additionally to my friends I've met there, but yeah. Sorry, Andrew. So, what you need is data invalidation, because invalid data, to a certain degree, is a time bomb. It wanders through your system, and the deeper it gets, the more damage it can do. And the sooner you catch it, the better is the response. For example, a web view has no problems of validating your data and giving a meaningful response. An ORM will just explode with some weird error, and the user gets a 500. So I think it's important to do things at edges. And other edges include dunder init or command line parsing. But I think validation is not enough. I'm sorry. I prefer my data and my business logic to rely on a simple canonical form. So the rest of the system can just rely on it. So what I'm talking about is that, for example, your business logic should not have to know about things like JSON or something like that. That's a presentation matter that should be kept outside. Now, other examples are date times, which you should just always transfer to UTC, save UTC, and recompute it on presentation. Or our good old friend Unicode. If you're using Python 2, I feel bad for you, but I'm sure in Ukraine you are much more sensitive to the problems coming from Python 2's implicit decode, which makes American libraries often unusable. So, yeah, charset encoding and decoding belong to the edge too. Now, there's a lot more time bombs, but I have no time. My talk is too long already. But yeah, and all this is well and good, but it's time to face a harsh truth. And the problem is that failure is inevitable. I've already told it about when talking about normal failures, because computers are complex. Distributed systems are complex systems of complex systems. So there is gonna be always failure. So in practice, your reliability will land on a spectrum. And the spectrum goes roughly from Twitter in 2007, where they had 98% uptime, which is 6 days offline, and NASA in 1969, which, despite a human error, managed to land on the moon. Because the software was actually robust enough to compensate for the error made by the human. Again, it was an astronaut is not stupid, but sometimes they do stupid things, and software was able to fix it. Now, the problem with NASA-style reliability is that you need an actual genius writing your software and kind of inventing software engineering while doing that. So you may have to scale down your expectations a little bit if you don't have Margaret Hamilton on your staff. Because if you do, I would like to apply for internship. So, if it's inevitable, what can you do? Well, you can minimize risks, like I showed you on the previous slides. You can prepare, and you have to deal. You have to deal with it. And this is kind of the bottom line of my talk, although I'm not by the end, by far. A long vacation, uninterrupted vacation, is a result of good failure containment and solid recovery. And this is what I'm going to talk next. So let's shift gears here a little bit. So first, you have to, if you embrace failure, you have to expect it. You have to actively expect it. And how do you do that? It's twofold. So first, you need to monitoring. You need to instrument your application and your systems. You need comprehensive monitoring for outages, instrumentation, error reporting. And I've talked about these things in the past 2 years, so I invite you to check out the videos on YouTube. And my taste still hasn't changed. I love Prometheus for monitoring and instrumentation. I love Sentry for error reporting. Both are open source. Sentry has paid plans. They are affordable. There's no reason to not use them. Now, the other part is that you have to expect failures in your applications. So the first part is simple. So like things like connection refused, or if a web API returns a 500. By the way, if you're writing web APIs, please never return a 200 with an error. That's what Tim Berners-Lee gave us error codes for. Now, there's a worst failure scenario though, and that is when nothing happens. So whatever you do, always put a timeout on it. And this can make a difference between a simple crash, which you can easily recover, and a deadlocked system. And anecdotally, one missing timeout in a database driver once grounded an entire American airline. So always put timeouts on it. Now, if you have timeouts and something times out, you shouldn't pester it all the time, because that gives a load to a system that may be overloaded, and that gives you very slow, useless requests, because every request that comes in has to wait the full timeout thing. And that's where the circuit breaker comes in. How many of you know the circuit breaker? Okay, so I'm going to explain it. So it's actually very simple and very cool. So it's running next to the client. It's just a class. It's not like a service or something. It's running together. Now, it proxies all the calls to a remote API and proxies the results back. This is called closed. You have to imagine like a drawbridge. It's closed, so the data is flowing. Now, if something happens, like a timeout, it changes from closed to open. And from this, usually don't do it on the first error. Like, it happens. Failure happens. So you do it probably after you get 2 timeouts or 3 timeouts. And then you change into the open state, and it will just ignore the remote API. And it will fail really quickly and telling the client the circuit is open, I have nothing to do for you. So then after a certain time, it changes again into half-closed. And in a half-closed state, it will send out a probe, a single request to check whether the API is now healthy or not. And if it succeeds, it goes back to closed, data is flowing. If it fails, it stays open, and we will not pester the remote API for another time. This is a very simple and very effective concept you can use for containing failures. So I've said adding more components is bad, which is true. But if it's the same component and you put another component which has a higher reliability than your own application in front of it, it might be good. And one of those components, and one I really like, is HA proxy. HA proxy is, and I'm not saying this lightly, good software. It never let me down. It's super stable, it's super robust, and it will just compensate for your shitty software, basically. So in the military, they say 2 is 1 and 1 is none. So, which means you should have at least 2 of everything, and the really critical things, you should have at least 3. Now, this concept made the internet almost unbreakable. The problem is that everyone is using the same DNS provider, and everybody is using the same storage service in the same region. But other than that, it's unbreakable. I feel like when I say this in America, it will be a lot more shame than in Ukraine, because I don't think anyone in here using din.com. So this concept works at any level. Network, you should have multiple switches, multiple routers, multiple uplinks. You should have multiple servers, obviously, but the parts of the server, like RAID systems. Multiple data centers, you should have them. So for example, for us, I work for a hosting company. Our most important system is DNS. So we have DNS distributed over multiple DCs that are independent from each other, which each have multiple uplinks. And of course, backups. You should have backups. You should have a lot of backups, and you should test them. Ask GitLab what happens if you don't test your backups. And if this is all it takes to lose all your data, you did not have backups. You need to have offsite backups. Okay? Now, if you want to make yourself dispensable, you must not be a knowledge silo. So, and Also, you yourself must not rely on remembering things when you need them. That's a big fallacy. People feel much smarter than they are in this thing. And it's been a staple of airfare security to have checklists for everything. For everything that can happen, there's a checklist from Boeing and from Airbus. Ask Andrew Godwin. He's an actual pilot. It's true. And most of us are not smarter than pilots. So, and if like things are going down, it's really nice to just have a list, you go down. And it doesn't have to be like a program for humans, because you should obviously automate everything you can. But it can be also communication things, like tell Sharon or talk to the other team. So, also, if you're writing shell tools, you should not rely on your shell history to remember how to use it. Just write a small README, because eventually you will try to use that same tool on a different server, and then it's kind of painful. So, yeah, usually a short README is just fine. Anyway, deal with it. How do you live in a world of fail? And I'm gonna just talk about applications, because operational response is a whole own talk. But so what do you do if your database goes down, or if a web service starts returning invalid results, or if you hit timeouts, like I've just said? So it obviously depends. But first, don't make things worse. Failure containment. Because in the worst case, you start a cascading failure, and in the end, everything just melts just because a Redis server went out of memory. That's not a good thing. So let's talk about something that's very simple but can have a very big impact, and it's retries. They're essential in distributed systems because transient failures are very common, but it's also very dangerous, because if you retry uncontrollably, English is hard, you can DOS yourself, so denial of service, or if it's a third party, you can make their life a hell, and you can probably land on some blacklist. That's not good either. So you need to back off. Now, how long do you back off? If you just ran into a deployment and the service was just booting, 1 second is good. If a server is overloaded and they need to add capacity, maybe you should try after 1 minute. If a switch is broken and someone has to go to the DC and replace a switch, or what I know, Amazon has to fix something, it doesn't make sense to check any earlier than every 5 minutes if the problem still exists. So what you want is to start with a small value and just let it grow exponentially. And that's what you do. But this is not good enough, because if all services have the same algorithm, they still hit the system at the same time over and over again and just possibly take it down every single time. So you want to space out your retries, and that's why you should add a jitter. A jitter is just a random number that you add to the timeout you've computed with your exponential backoff algorithm. It's simple, but this will save you from a lot of melted servers. Now, retries other than that are intuitive, kind of. But let's say you have a policy of retrying 3 times everything you do. And now we all read the orange news page, and we're having microservices. OK, let's add microservices. So 9 retries per backend. This is not good. But this is not microservices. This is medium services. Let's do microservices. 27. And at this point, you're DOSing yourself again. This is a combinatorial retry explosion. And imagine if C was flaky, just flaky, not broken, but flaky because of too much load. Now it's toast. So the simplest solution, the one I'm using, because my architectures are usually simple-ish, is that I retry only at the top. But it requires you to know what the top is, so the front end or something. And you can go much more complicated. You can have like per request retry quotas or budgets, so you know how often you can retry per request, but then you have to pass a context around, which makes it more complex. And this is a good example of complexity through microservices, which you would not have if you had just one big monolith. Now, there's a lot more to be said, like back pressure, like signaling to the upper services that that you're having problems to process the load, unbounded queues. Please do not have unbounded queues. Unbounded queues will do you a lot more pain than they're solving. And again, no time. There will be a link at the end. Next one, don't swallow errors. Because you want to have insight into the failures you are having. Otherwise, how do you fix them? How do other people than you who knows the system well fix it? And so if you're writing libraries and you do something like this, I hate you. How is anyone supposed to debug that? Oh, an error happened. Nice. OK, I just go home. And this is just the same. So if your library is doing this, please don't. You want to keep the error details. So again, if you're using Python 3, there's a very good solution to that. It's called exception chaining. And this will preserve the original error on the cause. And there is a solution for Python 2, by the way. There is in the 6 library that helps you to write Python 2 and Python 3 at once. There is a race from, how do you call it, function in there. So you can simulate that. So, OK, please, if you catch an exception and want to transform it in your own exception, always attach the original exception. Now, the next one might be a bit counterintuitive, but do not try too hard. If you have an application, it doesn't matter if it's a shell tool or a long-running server. If your app is unfit for work, for example, because your database pool just died on you, you could add hundreds of lines of handling this case. So you just stop processing and tell the user, oh, something's going wrong, and try to fix the pool. Or you add 2 lines. And more often than not, this is good enough. So report is obviously stand-in for whatever error reporting you're using. It can be log.exception, it can be Sentry, it can be rollbar, whatever floats your boat. And the nice thing is sysexit will still run your @exit handlers, so you can do cleanup. This is called crash-only software, and it's kind of an accepted idiom, but it's not as popular as I would like it to be. And there's more nuance to it, things like micro-reboots, things like that. But yeah, I like it, and I'm linking to the relevant scientific papers that explain it much better than I could in 1 minute. Now, what I'm saying, fail fast, fail loudly. A crash is better than a hang. Getting a user a 500 fast is better than to hang forever or until the browser timeouts. I mean, I'm sure you know it too. Just you click a link and nothing happens. And after a minute, you get an error from your browser. That's shitty. I prefer to just get the bad news immediately. And depending on your audience, it might be just really good to just give them the stack trace, because they may be able to fix the problem themselves instead of calling you while you want to lay at the beach and have a good time. Now, once you've done all of this, come to the final part. To make everything work, you have to focus on recovery. And this obviously only makes sense if we are talking about long-running processes. And the thing is, MTTR is king. MTTR is the mean time to recovery. And if you've accepted that failures will happen, and maybe even crash your software deliberately to have a quicker turnaround, it becomes much less important whether things go down, and much more important that they come up, and that they come up fast. And for that, you need to do 2 things. No humans allowed on recovery. So if I pull a plug in your DC and switch it back in, your infrastructure has to come up and be working. Otherwise, you have a problem. Because it doesn't have to be that brutal, but sometimes a rack loses power or something. If it doesn't come back on its own, and it needs human intervention, that's going to be really painful for you. And a prerequisite for software running in such an environment is that you must not have any expectations about the environment you're running in. So for example, you need a database. OK, try to connect to it on startup. But if it's not there, well, do your backoff thing and try until it's there, or crash. if your process manager allows for defining a backoff algorithm. I usually just go step by step through it and loop using a backoff algorithm until I get my database. So what I'm saying is, if I took a container, an image of your application and ran it on my notebook, it should do something sensible. It should not have any expectations whatsoever, what is present and what is not. So, what is the secret to a long, undisturbed vacation? Apparently, $9 Mai Tai in plastic cups, but at least the umbrella is not out of plastic. But embrace failure, expect it, minimize risks, prepare for it, and deal with it. So, this is all I have for you today. This is the link I promised. There's a lot of material for you to study. A lot of material I had to cut because 45 minutes are just too short. Other than that, follow me on Twitter, and if you speak German, get your domains from Vario Media, because they pay me to be here. Thank you very much. That's all.
Questions? No?
Oh, and by the way, I'm happy to talk to any of you, to discuss, to learn from what you've learned. So you don't have to ask me now, because I usually always get the questions wrong anyway. So I'm not sure I will give you a useful answer now. Just come to me.
I'll go first. Hello. So I have a question about one of the last points you made, automated recovery.
Yes.
So I have found in my experience at small and medium scales, having some human element in there for verification, say fall over to a secondary database, is useful. Would you say it's good to always be fully automated, or is there some element at a smaller scale that you say manual is sensible?
So we are talking about a little bit different kind of recovery. The one I meant in this case, because there's a lot of levels of recoveries. Some involve fixing data. And it's usually a bad idea to just let a program do something what it thinks is right, and then you don't have any data anymore. So yeah, I agree. In such things, in normal scale, a human should look before data is removed or whatever. But the server should come up on its own, and if it cannot work and it recognizes that the data is corrupted, it should notify a user to look at it. And that should happen automatically. That's what I'm saying.
Hello. I have maybe not question, like additional to your lecture. So to have a good rest in vacation, so you just need disable yourself from internet, and that's all, and you can relax.
Well, if it's your company, it works. Huh? But maybe then you don't have any customers anymore.
Okay. No more questions. Thank you.